So welcome back again. So today we will start with a new chapter, chapter 5, and this is register transfer level, or in short RTL design. This is the very popular design method. It is practiced in the industry, all right, to design a complex digital system. So what we will learn is this. You will be introduced to RTL design, right? Uh, so how to design a digital system, right? So there are two part, right? Which is the controller, which are the controller and the data path. In the RTL design, we have these two main parts. The controller will control the operation of the data path. All right, and controller is made of finite state machine. All right, we learned that in chapter 4. And data path comprises of register and processing unit. We also have learned that, all right, in the previous chapter. And we will look at RTL operation. What is the operation that involved in RTL design? We will look at the design methodology or the design flow, all right, where to start step by step until we get the design, all right. So what is RTL before we look at uh, and look into detail what is RTL design. So maybe we have a little bit revision of the design flow in digital design. So if you look at the lowest level of abstraction, is the physical view of the layout of our chip or the IC. So the layout is at the bottom of uh, the hierarchy. All right, if you go to the next level, so this will be the transistor circuit. All right, and next level will be the gate, the logic at the logic level. And we also have done this at the module level, all right, block to blocks. Okay, for example, the register is modeled as a box like this, 8-bit. All right, the ALU is model as this, all right, at the module level. So up next is the RTL level, all right. Similar to this, right? But we will look at on the connection and how the data is transferred from this, go to this, and back to this, or go to other register. All right, and later in the next chapter we will look at the even higher level, which is the algorithm level, right? So we are here in RTL, how we design this, connect this together to create a, a complete system. So why RTL? Because to build a complex data system at logic level is difficult. Yeah, it's hard at logic level, at gate or transistor or at gate level. At this level, we have learned that to create the circuit, a small circuit is okay, easy. If you have the Boolean equation, right? So you can straight away derive the logic circuit. But if your design is complex, yeah, you have 100,000 of gate, so it is very difficult already to design use at this level. So you need to go to the RTL level, all right, to design a complicated or complex circuit, right? So we view the system in terms of how the data is transferred and processed at higher level than logic. Yes, of course, at higher level than this one, this at module at RTL level. All right, we will look at how the data is transferred between this to this and to back to this or go to other register, right? So what is RTL? Actually, I have explained just now. Larger design are built by interconnecting the smaller module. All right, the last circuit is built by interconnecting this module together. All right, and we control the operation of that circuit. Yeah. What is the smaller module? So what we have learned before, which is the register, multiplexer, decoder, adder, register, and many more, right? So that is that what RTL is, yeah. So in RTL design, a digital system is partitioned into two main unit, which are this, yeah, the first one we call the control unit, or in short is CU, right? It's a circuit that generates the signal to control the process or operation of the circuit in the DU. What is DU? DU is the data path unit, data path unit, or in short we call it DU. So DU, what is DU? DU is comprised of register, buses, and processing and computing unit. So actually, we have learned this before this, right? We have learned how to design this kind of circuit already, right? So DU comprises of register, ALU, the processing or computing unit, and also the buses, right? How this thing is connecting together, right? That we call the DU, data path unit. And CU is this, is used to control the operation of this, all right? So it will generate the signal, the required signal to control the operation for this. All right, for example, this one is LDA. All right, so at what time LDA should be activated and not activate. All right, also for LDB, also the operation of ALU, because the ALU we have many operations, right? Remember, we have many, maybe we have add, we have sub, we have added many of logic operation. So it's controlled by this OP. But the question is, at what time eh, we should perform the add? At what time we should perform the sub, and so on. All right. So that will be controlled by this signal, and this signal is generated by the CU, the control unit. And what is CU? What is inside the CU? Inside the CU is essentially the finite state machine, FSM. All right. So we have learned in the previous chapter. We have learned in the previous chapter that the FSM can generate the control sequence. All right, just like uh, in the uh, in the last example of the previous chapter. All right, so at state 1, for example, so what is the output sequence here? At state 2, what is the output sequence here, what to do. At state 3, what to do, all right, to control this operation, the operation of this circuit, all right. So this one also we have learned in chapter 4. Okay, now we will combine these two, all right, to make a complete digital system, all right, to process the data. So what is RTL operation? What is the operation that we will use in RTL? All right. So there are three main elements. First is the register set. Of course, we need to have a register set. Register A, register B, or register 1, register 2, 3, 4, 5, and so on. All right. So we need to have the register. Number two, we need to have the operation that are performed on data in the register. All right. What operation that we will perform on the data? We want to shift the data. We want to add the data. We want to sub the data, or we want to do anything on that data. That is the operation. All right. And of course, the last one is the sequence of operation. Right. First, what we want to do. Second, what we want to do. And third, and so on and so forth. All right. The sequence. Okay. So we will do all of this in RTL design. Okay. So this is RTL operation that we will use in this chapter and also in the next chapter. All right. So also known as RTL notation. Right. So this is a notation or what we call it, just like a pseudocode in planning the operation of our circuit. All right. So just like we plan our program in C programming, yeah. So before we write the program in C programming, in computer programming, right? So we need to plan our program. So how to plan our program? To plan our program, we use pseudocode, right? We write the pseudocode. All right. First thing what we do, second what we do, third what we do, and we test. Maybe we test if the condition is met, we go to this way, and it's not met, it's false, we go to that way. All right. So same thing here. This is the notation, not a programming language. All right, not the programming syntax, but it is a notation that describes the operation of the data in our circuit. All right. So it is written like this. For example, if you have to register X and Y, all right. So if we have a register X and another one is Y, and we want to transfer the data. For example, this one is 8-bit, and this is 8-bit also. All right, the data inside this is in hexadecimal is AF. All right, so we want to transfer the data from here to here. So that we have AF in X. Yeah. So in digital or in computer, when we say transfer or move, all right, that actually means copy. Yeah. Okay, because when we transfer the data from this register to this register, we will see that the data is actually still remain at Y. All right, so at X will get the copy from Y. All right, because we just read the data from here from the bus. All right, and write in in X, and the data remain in Y. Just like when you learn microprocessor system, all right? When we move the data from register, for example, if you use a MIPS microprocessor or the ARM architecture, all right, you have R0, R1, right? So when we move the data from R0, R1 using the move instruction, all right? So AF move to R1. So the data inside R0 is still AF, all right? We not clear the data in there because, all right, in digital system, if you do want to do that, you need to do two jobs, so that is not necessary, all right. Okay, so when you want to clear, you can clear later on, or you want to put a new data, it will replace the data just like that, all right. So this is how we want to move the data from this to this, or actually it is copy. And in RTL notation, we will write like this. Okay, Y is transferred to X. All right, register the content of register Y is transferred to register X. Right, and always, yeah, the source operand, this we call it the source operand. Will be at the right hand side. This is destination operand will be always at the left hand side, right, in RTL design or even in computer, right. So this is how we do when we want to say that we want to move or transfer the data from Y to X. Next is this. If we want to connect the bus or the wire, the name for the first wire is M bus, for example. We want to connect M bus to R bus. All right. So this is how we do M bus sign equal and R bus at the left. Yeah. So means that M bus is assigned to R bus. Right. So this is just like this. So you have this bus, for example, 8-bit. This is M bus. So you want to connect all of this to another bus. Maybe this bus is like this. Yeah, 8-bit. So you want to connect all of the wire to this, and this is R bus. All right. So what we write is R bus, M bus. Okay. So that is how we do in RTL. Uh, Now how to clear a register? Clear a register means that we move zero or transfer zero to the register. All right. So means in this case is we want to clear register X. So we move zero to X. Right. So this is clear register. What if we want to add the content of register X to content of register Y? Right, and the result of this add operation is stored, is saved in register X. So this will be something like this. If you have to register, and you have the adder, right? So this is register X, this is register Y. You add, and the output is go back to register X. So this will be something like this. Right? The content of Y plus the content of X. Use the adder. So we add, and the result is go to register X. Okay. So this should be the circuit for this operation. And next is we want to transfer the data from one of the memory location, which is in this case is location 1000F into register X. Yeah? So this is the move of data where we move the data from the memory to the register. So again, last time we learned how to design the memory, right? So we can have the memory. So always the memory is drawn like the box with many location, many level. Okay. So in this bit, in this case, what is the size? So you have 5 hex digit. All right. So we have, and where, so let's say the location of 1000F is here, right? So before this should be 1000E, right? So for example, we want the data from this location, right? Our data is here. So we want to transfer this data to register X. So the data is 8-bit data, AF. We want to get the data from here and put it in our X so that we have AF in X. So the operation is this. All right, and this memory is named M, right? 1000FH. Okay, so means that we transfer the data from here, this location, to X. And this is also the transfer of data from memory to register. But in this case, it's indirect addressing, all right, where we use the data in another register as our address. All right. So for example, in this case, we have another register, which is Y, and the content of Y is this. All right. And Y is not 8-bit. Yeah. In this case, how many bit? 5 multiplied by 4 is 20-bit. All right. So let's say this one is this. So if we write like this, okay, means that here is actually the address. All right. This is indirect addressing. Right. So Y contain this. So we actually move the data from this location to X, right? Similar to the previous one, but now in the square bracket is the register, and the content of register is the address of the data. All right. Next is when we want to do shift, shift. So this is shift right, 1 bit. So if we want to shift the data in the register, so this is how we write X, the arrow, and SR shift right X, or we can just write like this X, using this symbol, greater than 2 times 1. 1 means that shift to the right 1 bit. Okay, if you want to shift 2 bit or 2 times, so this is replaced by 2 and so on. And if you want to shift to the left, so the symbol is less than 2 times, X less than 2 times, and 1 shift to the left 1 time. If you want to shift 2 times, so replace with number 2 or any number if you want, right? Next is the transfer of data also, but with condition. So if we want to transfer the data, for example, from y to x, but based on the condition that we set. For example, we have the condition here. If the condition is true, then we move the data from y to x. But if condition is not true, all right, false, the condition is not met, we do nothing, all right, or do other things, depend. All right, so this is how we will do this a lot, later on. Right, we move the data if the condition is true, right? Next, also move, transfer y to x, and this is actually represent the state. Means that at state s0 we move the data from y to x, right? And the last one is moving the data also, right, in the state s0, but with condition. All right, this is condition. This is example actually. So if condition A and B is true, means that if A and B equal to 1, you move the data. So here can be anything actually. This is condition, just like this, but we have the state. We do this in state S0, for example, right? So this is the common RTL notation that we will use throughout this chapter 5 and chapter 6. So there are more RTL notation, but this is the common one that we will use. Okay, so let's look at this example, all right, for better understanding of this RTL design. So let's, for example, we want to do this, figure below. Actually, this is the figure, the next slide, right, shows the data path functional block diagram of a digital system. Suppose that we want to execute the operation according to the RTL code below. All right, this is the code. All right, you can see that this is in sequence. All right, just like we look at here, the sequence of operation. All right, and this we have all of these element, right? The register set, the operation that perform on the data, and the sequence, right? So if you look here, so we have the register, rec 1, rec 2, rec 3 is the register set. The operation is the move operation. We move data from here to register 1, move data from register 1 to register 2, move data from register 2 to register 3. Right, that is the operation that we perform on the data. And this is the sequence. Number 1, we do this. Number 2, we do this. And number 3, we do this. All right. So the operation is easy. The first operation is to read the data, data into register 1. Right. And the next one, we transfer the data in register 1 to register 2, and the last operation is to transfer again the data from register 2 to register 3, right? So this is the explanation, just like what I explained just now. So let's see the circuit here. So this is data path. yeah, where we have a set of register, we have the multiplexer here, and we have the bus. All right. So what we want to do is we want to transfer the data here into register 1. All right. And from register 1, we will use this multiplexer to select what signal will go through. All right. So that is why we learned how to design the multiplexer in chapter 2, right? So we will use here. So the data in register 1 will go through this based on this SEL2 signal. And this is 2-bit, right? Because this is 4 to 1 marks. Okay. So we can see that this register share the same bus. So this bus is called data out. All right. So this is the same line, same bus, and the size is 4-bit. Okay. So in digital design or computer design or microprocessor design, we always share the bus like this. All right. We don't have separate bus for every register because that is very costly. All right. So we always share the bus. So how to share the bus? Eh? So the bus is just like the highway, right? But the difference is that the highway you can have many different type of vehicle. You can have car, can have bus, you can have truck on the road at the same time, right? But the difference is for the computer buses or highway is that you cannot put different data at the same time. For example, you want to put the data from rack 1 and rack 2 into the bus. Okay, so this data, because the data is just a voltage, yeah, electrical voltage. So it will interfere each other. It will corrupted. All right. So the data will interfere each other if you put different data at the same time. So what you need to do is you need to make sure that at one time only one data is allowed to enter the bus or use the bus. Right. So this is one of the method that we isolate the data from many register or many sources that can enter the bus. Uh, at one time, only one data is allowed to enter the bus. For example, in this case, right? Uh, if we set this to 00, then only the data from REG1 is allowed to enter the bus. All right. If we set to 01, only this data can go to the bus. And if we set SEL2 10 is allowed to the bus to go to the bus. All right. So this is only one way to implement the bus. Another way is this. We use the three-state buffer, all right, to isolate the data from the register to the bus, right? So in this case, for example, if en this three-state buffer en is equal to 0, means that this wire is not connected to the bus. All right. If it is 1, enable 1 equal to 1 and the rest equal to 0, then this one will go to the bus. All right. So this is one way, and actually we have another way uh, where you can use decoder, right, to uh, to select the data where you can have something like this: register 1, three register, just like that. Okay, we have 3 register, and we have this register. We can have the enable read enable. All right, just like what you did in your assignment last time. All right, you can enable whether you can get data from register 1 or register 2 or register 3 based on this enable register signal. So you can have the decoder. All right, so this decoder is uh, you can have 2 to 4 decoder. So this can be connected to this can be connected to this connected to this, and this is data out, and data out, right? So if 0 0, so this is 1, and this should be 0, and this should be 0. So this will enable this register, enable read for this register, and you can get the data from this. And this one, the data is not here. All right. This is also another way to implement the bus. Yeah. All right. But in this example, we use multiplexer to implement the bus. Okay. So now remember, what we want to do is to transfer the data from here to register 1, and from register 1 we go to register 2, and from register 2 we go to register 3. All right. How to do that? Uh, so the RTL code, yeah. So just like what we have learned just now. So this is RTL code, and we can rewrite the RTL code like this. Okay, using this uh, notation where moving data from data 1 from the outside from here into rack 1 is in S0, the state S0. The next state, we move the data from rack 1 to rack 2, and the last state, we move the data from rack 2 to rack 3. All right. So how to do that is based on this sequence. All right. For example, in state 0, in order to do that, what we need to do is that we need to set the signal, the control signal here, at the right time, at the correct time, right? So to do this, to move the data here to this register, what you need to do is to set this signal to 1, such that the data here can go through this multiplexer and go to rack 1. All right. So to go to rack 1, you need to enable this LD1, right? This is load. All right. If you not activate this LD, LD, so the data cannot go into this register. Means that to do this, what you need to do is to set SEL1 to 1 and to set LD1 to 1. All right, and should be this one. And the other signal is don't care actually. We put it at 0 0. This one is 0, uh, 0 and 0. All right, so we're not loading any data into rack 2. All right, so this one should be put at 0. LD3 should be put at 0. This one, all right, you can have 0 0 or 0 1, doesn't matter. Okay, but the important one is that SEL1 must be 1, LD1 must be 1. Yeah? So to do that, we will create a table, what we call the register transfer level RTL control sequence table, or in short, is named as RTLCS table, like this. All right. So the RTL code, we have this code, and we write or we list all the activated signal in order to do this operation, right? So in S0, we want to transfer the data from here to here. So just like I said, so LD1 must be 1, SEL1 must be 1. So here you can see that LD1 is equal to 1, LD2 equal to 0, LD3 is equal to 0, SEL1 must be equal to 1. SEL, and this SEL2 is 2-bit because this is 4 to 1 multiplexer. So this is 2-bit, 0, 0, 0, 1, 1, 0, and 1, 1. So we have 2-bit, bit number 1 and bit number 0 here, 0, 0, right? So this will definitely move the data from here to here. And the next operation is to get the data or to move the data from here into REG2 in the next state. All right. So to do that, this one must be 0, 0. All right. So that this data from rack 1 will go to the bus, and to load the data from the bus into rack 2, this one must be 1 and the rest should be 0. Right. So that's why we have here 0, LD2 must be 1, and SEL1 and SEL2 0, 0, 0. All right, 0, 0, and the rest should be 0. Okay, so this will transfer the data from here into rack 2, right? And we see that here signal activated, LD2 must be 1. This, all right, activated star here means that inverted, or not. All right, means that this is 0. This one should be 0. Must be 0. Must be 0, 0, 0. All right, and the last operation is to move the data from here into here. All right, so again here this should be 0, 1, and LD3 must be 1 in order to get the data from here into the bus and read the data from the bus to rack 3. So that's why we have here LD3 must be 1, and this should be 1, 0, 0, 1, sorry, 0, 1, right? So LD3 1, and this one is 0, 1. So this is the signal that should be activated at S0, S1. These are the signal that should be activated, and here the signal is this, right? So we have learned how to create something like this using the finite state machine, right? So we can actually do that, right? Write the Verilog code to describe or implement this sequence. Okay, so now we want to write the code for that. Here we have the code example, but I want to show you in quarters, right? So that we can look at the simulation, the result. All right. Before that, any question? Okay, so if no question, we will look at this. Yeah, the quarters, how to write the code to implement this, and also we need to have this, All right. So to write the code for this one is straightforward actually. All right, because we have everything here. So let's have this, and okay. All right. So you want to write the code for this first. You can write together. So you create a new project. Uh, this is RTL chapter 5. So this one we call it data pass unit for example 5.1. All right, so that the name is here, and this should be done. Okay, so we write the code for this. We have the module, yeah, and remember that when we write the code for to describe the digital circuit, yeah, we need to make sure that our code is synthesizable. So many of you ask me through WhatsApp, all right, that your code has too many warning, yeah, when you compile your design, all right. Why is that happen, all right? So is it because your code sometimes is cannot be synthesized into a digital circuit, all right? Because we need to remember that when we write HDL, Verilog HDL or any other HDL, VHDL or Verilog, uh, you need to remember that the code that you write is to describe a digital circuit, not a sequence of operation, just like in C programming or any computer programming. It's different. So you need to make sure that your code is directly represent your circuit, right? Can be synthesized into the correct circuit. If it is cannot be synthesized into a circuit, you will get many warning. All right. Maybe you will have the connection problem. All right, something like that. So for this, because I want to design this, so I have to have this design here, all right, so that I can write the code exactly that represent this circuit. So again, yeah, we have the module, and the port list here. So we need to list all the port. The port means that the input and output. So where is our input and output? So this should be the input data in LD1 R reset the clock. Yeah, the output should be data out. All right. So let's have that. So you will have the clock. You will have the reset. Uh, and all the control signal here, SEL1, SEL2, all right, LD1, LD2, LD3, LD, LD1, LD2, LD3, all right, data in, data in, all right, continue here. You have data out, And anything else? No, already actually. But I want to include another one. This is for simulation because later on we want to see what is inside rack 1, rack 2, rack 3. So if we not set this as input output, then we cannot see what is inside this register. So what I want to do is to add this to the output, here to the output, here to the output. All right, just for simulation purpose. Yeah. So this one, rack 1. All right, I add this output port, so that later on in simulation I can see what is inside rack 1, rack 2, rack 3. Okay, so I just set list rack 1, rack 2, rack 3 here also. Okay, now we list all the input. So we have input, the 1-bit input is should be this, except LCL2. This is not 1-bit, this is 2-bit. SEL2. And also we have this data in input, which is 4-bit. Data in, data in. And also we have, any other inputs? Data in, no, right? Data in. Now output is 4-bit. Oh. And this should be in rack data type also. Why? Because we later on the data out, right, must be declared as variable, because we will use always block, yeah, to define this multiplexer, and also to define this rack 1, rack 2, rack 3. So all must be declared as rack also. All right, so that should be the port list. Now we want to describe maybe this multiplexer first. Okay, so to describe this multiplexer, we can use either behavioral modeling or data flow modeling. So let's use data flow modeling. So in the example here is using the behavioral modeling. Yeah, we use always block, but in this example I use data flow modeling. You can do that also. And if you want to use data flow modeling, and also this one, we need to have the signal name, the wire name. So need to label this as maybe we call it R1 in. All right, yeah, R1 in. So and this one must be declared as wire if we want to use the data flow modeling. And this is 4-bit R1 in. All right, so that we can use here assign R1 in. Okay, so this will be based on this select 2, select 1, right? This uh, data in, or from another one is what? This, yeah, data out. All right, so this will give you the first multiplexer. Let's name this as box 1. All right, now after we have the box 1, we want to describe this red 1. So this is for red 1. We can use the always block, always, and this is positive edge. All right, positive edge triggered uh, clock, and we have a reset, positive reset also. Okay, so that is the this so we look at the reset, right? If reset, so the output of this register, which is reg1, should be equal to 0, all right? Or in other words, we call it 0 is assigned to red 1, right? But if not reset, we will read the data from the outside here, R1 into the register, but it depends on this LD1 signal, right? So if LD1 signal equal to 1, then the data here will go to the register. So we can have else if LD1, right? Red 1 should be what? Should be R1 in this signal, right? This signal. Okay, that's it. So this will be this register. Okay, so you can have another one, another register, and it's actually a similar register. So you can use, you can have, you can copy here, and this is the same clock, same reset, and except that this is rec 2. If reset, rec 2 equal to 0, and this is LD2, rec 2, and the input for this is only from this data out. So it should be data out. All right. So you can see that this code, yeah, is directly synthesized to this, the synthesizable code. This is called synthesizable code. Means that everything here is directly represent this. This represent this. This represent this. This represent this. Right. And the last register is this. Register number 3. And just use the same clock and the same reset. So we just rec 3 equal to 0 if reset. LD3, so rec 3 is, yes, from the data out as well. So this will represent this register, right? And the last one is the multiplexer. Box number 2, right? So here we can describe using behavioral easier because we have many input 4. So we can use case statement here. Always block and a list in the sensitivity list. So you have this cell 2, you have here rec 1, rec 2, rec 3 as the input. As the input. All right, and now you can use case statement. All right, if cell 2 equal to 0, 0, so the output here should be from rack 1. So you can have case what? Case cell 2, right? So if cell 2 is equal to 0, 0 or 2 bit, yeah, the size is 2 bit, 0, 0. So the output should be the data out, yeah, here data out should be equal to rack 1. Now, if you look carefully here, the register, the sequential circuit, we use the non-blocking assignment, yeah, and this is combinational block. We use the blocking assignment, all right? Remember in chapter 3, we learned this. So for 0, 1, data out should be from rack 2, and from 1, 0, data out should be from rack 3. And we should have this also 1, 1. You can write 1, 1, or you can use default, right? Means that other than this, yeah, that out should be in this case is not connected, so we can use this is 4 bit, right? We can have this is that not connected, is that, or what we call it 3-state buffer, right? We have some kind of, or we create the 3-state buffer here, all right? And case, anything else? No, we have done, all right? So this is the circuit, and we can save this in here, save, and just try to run the synthesis and analysis. And we have 6 warning, right? So we have, yeah, many warnings, so you need to have a look at that warning, because it may uh, give you problem later on, although there is no error, but warning is not good, right? So let's look at the warning. Right, the first one is about the license should be okay, can be ignored. This is 3-state node, do not directly drive top logic pin, top level pin. So what is that? You can expand. So this one, rack 2, rack 1 into an OR gate. So it will create OR gate because of this actually, all right? Because we have the 3-state buffer, it will create the 3-state buffer for us. So let's say if we put this as don't care or 0, right? It should be no problem, right? Because it's directly create this multiplexer. Right, we can see that there is no error warning anymore, right? Only the license warning, so should be no problem. But actually we don't care here, because this is actually not connected, so we can use 3-state buffer, and this warning can be ignored. All right, this is no problem, because it will create the extra circuit for us, to make sure that this is not connected. So should be no problem in this case. Okay, so all right, so you can see that some warning can be ignored, but you need to know what is that warning. All right, in this case we know exactly what is the warning, so it should be no problem. Okay, so this is our data path unit, and now we want to create the next one, which is the this, yeah, this, all right, the control unit, which is the actually the FSM, all right, that can generate this output whenever we are in state 0, and when we are in state 1, will generate this output, and when we are in state 2, we will get this output, and this output will be, yeah, will be connected to this, right? Will be connected to this so that it will activate the right signal at the right time. So for example, at S0, it will move the data from here to here based on the signal activated here. All right, S1, it will move the data from here to here. S2, it will move the data from here to here. Okay, so that is the control circuit that we want to create. So we will need this also, and we can have a new one. Okay, let's have in a new folder. The name is CU. Okay, control unit, and the name is this. Actually, we can finish this and log module. Okay, we have clock. We have our reset because the FSM, we need the clock and we need the reset, and the output of this FSM is actually this LD1, LD1, need LD2, you need LD3, you need SEL1, and also SEL2, right? Maybe I add another signal, which is the state, so that I can see the state in the simulation. All right, this is for simulation only, yeah, the state. Input, so we have only two input, clock and reset. The output, we have this for the 1-bit output, and we have 2-bit output, which is the, and this should be in red data type also, because we will describe using a behavioral modeling, and we have another output which is 2-bit, and also the state is how many bit the state. All right, so we need to look at this. Here we have how many states? We have 3 states. All right, when we have 3 states, so we need to have how many flip-flops to represent or to create this finite state machine. So we need at least 2 flip-flops, right, to represent up to 4 states. So we can have here also, this is 2-bit. All right, the state is 2-bit, and now we want to create this finite state machine. We want to describe the circuit for that. Okay, so to do that, we need to have the block diagram for our finite state machine or the control unit. So we should have something like this. The state register and the output logic and the next state logic, right? Remember FSM? So we will need to have next state logic. We need to have state register we need to have output logic. All right, and the connection is just like this. And remember, you need to have the feedback here, and this is more type finite state machine. Okay, and what is the size for this one? Of course, 2-bit. 2-bit. This one is 2-bit. What are the output? So you have this output 1, 2, 3, 4, 5, 6. Okay, so you have LD1, you have LD2, LD3, you have SEL1, you have SEL2 bit number 1, SEL2 bit number 0. Okay, do you have any input? No, this ASM is not depend on any input. It will change the state just after this operation. One clock cycle, the next clock cycle will be this one, the next clock cycle will be this one. All right, so there is no input to this finite state machine. All right, the only input is the clock, and we will use negative H clock. All right, you will see here the register is using positive H, but in finite state machine here I will use negative H. Why? I will explain later. All right, why I use negative H here. Okay, and also we have the reset signal, which is positive H also. All right, and this is the circuit that we want to create. Okay, so we need that, and the name for this signal is called next state, and this signal is called state. All right, so in here we need to have this signal, right? And the size is 2-bit, and it is in the rect data type. Next state, yeah, and this one state is declared here already, so should be no problem. Next state, and because we want to create the finite state machine, so we need to create the state name using parameter, and this is 2-bit, name as 0, right? As 0 is you can use 2-bit, as 1, and the last one is as 2. All right, that's it. Okay, now we want to create this state register. Okay, using always block, and this is negative H, right? And positive is reset for this. So if negative, right, positive, yeah, reset. If reset, so the output is what? The state should be equal to 0, or in this case is when reset we are at state as 0, else Okay, if not reset, state is equal to, should be the input of this flip-flop, right? Next state. Okay, so this should be this state register. Now we want to create the combinational circuit, which is this one and this one. All right, we call it next state and output logic. Okay, using the always block. Right, now the sensitivity list. So for this one, the input is this, or sensitive to this signal, so we call it state. And this one also sensitive to the state one, the state, so should be no problem. Only state. All right, and we can use case statement. All right, so if case for the state, so if we are at 0 0 or state at 0, what happened? If 0 1, what happened? If 1 0, what happened? So we can use state case, yeah, case state. All right, so when we are at S0 or 0 0, so what we should do? We should output the right this circuit, this signal based on this. All right, so we have many, so we can have something like this. Begin, we have many statements, so we need to use begin. All right, LD1 should be equal to 1 in this case, right here, and LD2 should be equal to 0. LD3 should be equal to 0. SEL, this is a small letter, sorry, this is should be small letter based on this cell 1 should be equal to 1. SEL2 is 2-bit. SEL2 is 2-bit. So what is it? 0 0, right? So it should be 0 0. And also when we are, this is output, and also we need to define this. All right, so the next state when we are at S0, the next state should be S1. So next state should be S1. All right, and we should have n here. Okay, so this is for S0, and we can have the S1. We can have this S1, replace this with this 0. This should be 0. LD2 must be 1. LD3 must be this one, yeah. LD3 must be 0, 0, 0. All are 0. 0. Okay, so 0. And the next state should be, after S1, we go to S2. Okay, so that's it for this. Is it the same? 0 1 0 0 0 1 0 0 0 0. Okay, and the last one is S2, and this should be 0 0. LD3 is 1, select one is 0, and here it should be 0 1. Okay, should be 0 1. And the next state we repeat the operation for the, just go back to S0. All right, and we have 3. And again, you need to remember, if you use case statement, you need to have all the combination of this, 0 0 0 1 1 0, and you need to have 1 1. If not, you will have a warning later on. All right, means that you create a memory here. All right, so you can use default, and if other than that, we put everything to 0. All right, and we stay at state 0, should be okay with that. Okay, and is here. Anything else? No, should be done. And module done. So this is the our this represent variable output to represent this, and the output is based on this. All right. So let's save this and try to synthesize this. Okay, now we have 3 warning. All right, again we have 3 warning, and we should have a check, have a look with to this warning, and this is the warning, and of course the first one is the license, and output pin are stuck at VDD or ground, means that there is, or there are output that is always 0 or always 1. All right, so we need to know which one, and is this okay or not okay. So we should look at this. We can see that here SEL2 bit number 1 is stuck at GND, ground, means that it's always 0. Is that correct? Do we want this? Do we want this? Because the software, when it's look something stuck at 0 or never change, it will give us a warning. So whether we want that is part of our design or not, depend on us. All right, so in this case, so where is SEL2 1? So should be this SEL2 1. And when we look at here, it is yes, definitely always 0 0 0, always 0 or always stuck at 0. So the question is, do we want this? Yes, definitely we want this. So should be no problem with this. All right, because again, in our case, we don't have this 1 1. So SEL2 bit number 1 never go to 1. All right, in our design, because this one is not connected. All right, so it's always 0 0 0. We never use these two, so we only have 0 0 and 0 1. We don't have any option in our this. All right, because we just move the data from here to the bus, here to the bus, but not rec 3 to the bus. We're not doing that. That's why we have this 0 0 0 0 0 0 0 0 1. Yes, this is correct, so should be no problem. All right, so we can, means that this warning is okay for us. Okay, so now we want to connect this together to create the complete design. All right, so let's do that. But before that, we are here. at 10:45. So maybe we have a break for 10 minutes and come back. We try to combine this DU and CU together, and let's look at the simulation result.